Today we look at oblique triangles, the ones that aren't right triangles. In order to find all the sides and angles of these triangles, we'll use a couple of rules. The first one we'll study is called the law of sines. Join me for Precal online now. In this section, we begin to look at triangles that are not right triangles. So in general, the Pythagorean theorem will not be used for triangles of this type. Our first lesson is over the law of sines, but let's take an overview of what we're looking at here. First off, an oblique triangle is a non-right triangle. And how do we characterize the triangles that we're going to be looking at in the rest of this chapter? Well, they're denoted by ASA, SAA, etc. The A stands for angle, and the S stands for side. Now, these descriptions here on the left are not just giving us the quantity of the particular items that were given to solve for the rest of the triangle, but they're also telling us sort of in what layout, in what order we have. So the first one is ASA. That means there are two angles, because we have the two A's, but you can see that the side symbol is in the middle, so we call that an included side. So it's not just some random side that we're given, it's the side that's between the two angles that we're given. And to solve the rest of the information about that triangle, we'll use the law of sines. If you have SAA, then you still have two angles because you have two A symbols there. And you have a side, but notice that the side is sort of on the outside. So this is a non-included side. And this uses the law of sines. Next we have SSA, which has two sides, and the angle symbol is now not included, so it's a non-included angle. Since it's non-included, meaning it's not between the two sides, then it necessarily has to be opposite to one of the sides that we're given. So that's sort of important to remember. And this one also uses the law of sines. I'm going to put a little asterisk by this one because this one is going to be the toughest one, and it produces what we call the ambiguous case. And we will talk extensively about the ambiguous case on the coming pages. The last two, side angle side, that's two sides with an included angle. So there's an angle in the middle of the two sides that are given. And for this one, we use the law of cosines. And if we have side, 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 that means we have three of the sides given and with none of the angles. And to start that one, we use the law of cosines. So let's look at the law of sines formula. It says for a triangle with sides A, B, and C, and the opposite angles, capital A, capital B, and capital C, respectively, then the sine of A over little a is equal to the sine of B over little b, and the sine of C over little c. So let's just draw a triangle here. And we can have A, and the side across from that is little a. We can have B, and the side across from that is little b. And then angle C, and the side across from that is little c. What the law of sines is telling us is that the ratio of the cosine of an angle to its opposite side is constant for the particular triangle. And so you can create these ratios just however you want. Now, the law of sines is always presented as the A1 is equal to the B1 is equal to the C1. But in reality, we only use 2 at a time. But all 3 of them are going to be equal to the same ratio, and so you pick whichever 2 you want to use. Example 1. Solve the triangle. Angle C is 65 degrees, angle B is 38 degrees, and B is a side of length 7. So first off, what type of triangle do we have? Well, we have 2 angles and the opposite side. So that would be side, angle, angle. And let's just draw a little picture here. Now the pictures that we draw are usually not very accurate because we don't have all the information. So at best, they're just used to sort of organize things. We try to draw them as best we can, but they're not always accurate. So I've labeled A, B, and C. Angle B is 38 degrees, that was given. Angle C is 65 degrees, that was given. And side B is 7, and that's the opposite to angle B. And now we want to find the rest of the information. The information here that we need is angle A, and side C. The easiest one to go for first is angle A, because we know that the sum of the angles of a triangle is 180 degrees. I can just subtract the 2 angles that I know from 180, and that's 77 degrees. So I'll mark that. I'll sort of denote derived information in a different color. Next, let's go for little c. Little c is opposite of the 65-degree angle, and we always want to use a pair of information that was given to us if possible. The pair of information that was given to us in the original problem is the B pair. So we know the angle B and the side B. So I'm going to use that to start with. So the angle of sines tells us that the sine of 38 degrees divided by the length of the side across from that angle, 7, is equal to the sine of the angle, 65 degrees, divided by the length of the side across the triangle from that angle, which is little c. So that's what the law of sines tells us. Now to solve this, we're going to cross multiply. So the c is going to cross multiply into the numerator on the left, and the 7 is going to cross multiply into the numerator on the right. That gives us c times the sine of 38 degrees is equal to 7 times the sine of 65 degrees. And now to solve for c, we divide both sides by the sine of 38 degrees. And c is equal to 10.30. Let's go ahead and round everything to 2 decimal places here. Lastly, we need to figure out the length of side A. So this is going to be the sine of 38 degrees divided by 7. Again, I'm using an original pair of information because that contains the most accurate information about the triangle. That is equal to the sine of 77 degrees divided by little a. Cross multiply, and you get a times the sine of 38 degrees is equal to 7 times the sine of 77 degrees. So a is equal to 7 sine of 77 degrees divided by the sine of 38 degrees. And when you work that out, you get 11.08. Let's look at example number 2. Solve the triangle. A is equal to 22 degrees, C is equal to 45 degrees, and little b is equal to 9. So I'm going to go ahead and draw the triangle. And we'll have angle A, angle B, angle C. We're given that A is 22 degrees, C is 45 degrees, and B is 9. That's the side length on the bottom here. What type of triangle do we have? Well, we have two angles and the included side. Two angles and the included side. So that would be angle, side, angle. For angle, side, angle, we use the law of sines. So first I'm going to figure out what angle B is. That's 180 minus 22 degrees minus 45 degrees. And that's equal to 113 degrees. Next, I'm going to figure out little a for a side. And so I'll use the B pair to start with. So the sine of 113 degrees divided by 9 is equal to the sine of 22 degrees divided by little a. Cross multiply, and we get a times the sine of 113 degrees is equal to 9 times the sine of 22 degrees. Divide both sides by the sine of 113. We get 9 sine of 22 degrees divided by the sine of 113 degrees. And when you work that out, you get 3.66. Lastly, we need to find side C. So I'll start again with the B pair. Sine of 113 degrees divided by 9 is equal to the sine of 45 degrees divided by little c. Cross multiply, we get c times the sine of 113 degrees is equal to 9 times the sine of 45 degrees. Divide both sides by the sine of 113. We get c is equal to 9 times the sine of 45 degrees divided by the sine of 113 degrees, which is 6.91. Now let's turn our attention to the ambiguous case. Given two sides and an opposite angle to one of these sides, there are 4 different possibilities. So first let's analyze this. This is going to be side-side angle. And let's say that you're given little a, little b, and the angle capital A. Now these letters can change. So what we're doing here is sort of the theoretic part. So just be cautious of that when you do the assignments and the homework. But if this is the scenario, then we have a vertex here for A, and a ray that runs off that. Then, since we know angle A, this is fixed. So this angle is now fixed. And then we're going to go ahead and say that this leg, this side of the triangle is the side B. And the question that remains is, since all these parts are fixed at this point, is it possible to draw A so that it actually forms a triangle? And if it does, what type of triangle does it form? And how many triangles could I possibly make given this 3 pieces of data? So that's the question. The way we solve this is essentially comes down to how long A is with respect to the distance from that point to the ray down here. So the shortest distance from this point, which is going to eventually be vertex C, but it's just a point right now, is the shortest distance from that point down to the ray is the perpendicular distance. And since it's a perpendicular distance, it's the height of the triangle that would be formed if this works. So we call it H. And we know that the sine of angle A, using the stuff from right triangle trigonometry, the sine of angle A would have to be the opposite side, which is the height H, divided by the B, which would be the hypotenuse of a right triangle that's formed over here. That means that H is equal to B times the sine of A. So the height is completely determined by 2 pieces of the data that we're given, the B and the angle A. And we're going to use this formula to compute the height and then compare it to the A to see if we can actually form a triangle. So let's do that. Here are the cases. There are 4 cases. Case number 1. Suppose that the A is actually smaller than the height. So let me draw a little diagram here. So we would have angle A, the B, the height here, that is H, and then we would attempt to attach side A and bring it down to form a triangle. But if A is smaller than the height, then there's no way it's going to reach down to the leg. It's not long enough. The height is the shortest distance from that point down to the ray, and if A is smaller than that, then it's not going to reach there at all. So our conclusion here is that there is no triangle formed. And the answer to questions like that would just be no triangle. Case number 2. What if the A is equal to the height? Well, let's draw a similar picture here. So here's our B, here's our A, here's our height. And in this case, what if the A is exactly the same? So not only is this the A, it's also the height. Well then, we're in business, and we have one right triangle. Because the length A is going to come off that vertex at the top, it's going to intersect the ray at the bottom in exactly one point, and that one point where it intersects is called the foot of the right angle there. The foot means that's where it intersects at a right angle. And so you get one right triangle. Third case, what if H is less than the A, which is also less than the B? Well, this is where it gets a little complicated. Let me draw the triangle. Here's the B, here's capital A, here's the height, there. And now what we do is we have the length A is bigger than the height. So that means we do at least produce this triangle where the A can come to sort of the outside of where the height is. But what you have to realize is that the lengths that come off the vertex at the top, the shortest length to the ray is H. And then as I create these links moving the intersection point on the ray toward the angle A, these get successively larger as you move toward angle A. So H is the smallest, and then because this is a ray and not a line, the largest I could use is B. And so A is a length that is between this H and this B. And that means there does exist a length A that will perfectly intersect the left side of the height to form a different triangle. So what we have here are two triangles. It's a two-triangle situation. And when you encounter a problem like this, you're required to solve for both triangles because you're giving all possibilities. Let me go ahead and highlight where these triangles are. The one that's sort of hard to see is right here in this light blue color. That's one of the triangles that has angle A, and side B. And the other triangle would be the one in brown here, like so. Still, angle A, and side B. So that's the two triangle situation. Our last case is when the A is greater than or equal to the B. In this case, the A is going to come off the vertex, and it's longer than B, so there's no way that it can come out to the left here. Let me try to draw that. There's no way, because then it would never intersect over there. But it is long enough to intersect the ray, because the ray goes on forever. Let me draw that out a little bit. And so we do get one triangle. And it should be mentioned that if the A is bigger than the B, then it is clearly bigger than the height, because the height has to be smaller than B. And those are the four cases. So what you want to do whenever you have this scenario with side-side angle is you want to analyze which case you have and then approach the solving of the triangle from that point of view. Let's look at example 3. Solve the triangle. C is equal to 4, B is equal to 7, and angle C is equal to 50 degrees. So we have a pair that's given here, the C pair, and an extra side. So that is side angle. That's the ambiguous case. So we need to determine what type of triangle we have. Either none, one right triangle, two triangles, or just one big triangle. So to do that, let me sort of draw a little sketch. So we're going to have 50 degrees here at angle C. The side adjacent to the 50-degree angle is going to be the 7. And then what we want to try to do is pull the side that's length 4 off the side of there. And the question is, can I even do that? So let's draw the height. And the formula for the height is going to be 7 times the sine of 50 degrees. So I always just sort of see a little right triangle here with this angle, that opposite side, and that hypotenuse. If you put that in the calculator, 7 sine of 50 degrees is 5.36. And therefore, the 4 doesn't quite make it down to the ray on the bottom. So this is greater than 4, and that's no triangle. So side C is just not long enough to reach down to form a triangle, and so we get no triangle. Let's look at example 4. Solve the triangle. B is equal to 10, A is equal to 6, and capital A, the angle, is equal to 24 degrees. Again, we have a pair and an extra side, so that is side angle. So we have to check the triangle. Let me draw a little sketch. So we're going to have 24 degrees. We're going to have a side of 10, and then the question is, can we hang the 6 off of this side, off of this vertex over here? To do that, let's bring in the height. and the height is going to be 10 times the sine of 24 degrees. If you work that in a calculator, you get 4.07. And then the comparison is that 4.07 is less than side A, but it's also less than side B. This is the third case where there are two triangles. So we must solve for both triangles. So triangle number 1. So we have 24 degrees, angle A, a side of 10, and a side of 6. So first, let's use the law of sines and go after the angle B. So sine of B over 10 is equal to the sine of 24 degrees divided by 6. To solve this, cross multiply. We get 6 times the sine of B is equal to 10 times the sine of 24 degrees. Divide both sides by 6. We get the sine of B is equal to 10 sine of 24 degrees divided by 6. And B is going to be equal to the inverse sine of 10 sine 24 degrees divided by 6. Work that in your calculator, and we get an answer of 42.68 degrees. Now that we have two angles, we can get the third angle using the fact that the sum of the angles of a triangle is 180 degrees. And that third angle is 113.32 degrees. So let's find side C. So we're going to have sine of 24 degrees divided by 6 is equal to the sine of 113.32 degrees divided by little c. Cross multiply, and we get c times the sine of 24 degrees is equal to 6 times the sine of 113.32 degrees. Divide by the sine of 24 degrees, and we get c is equal to 6 sine 113.32 degrees divided by the sine of 24 degrees, and that's equal to 13.55. And that's all three parts that we're missing of the first triangle. So now we have to get the second triangle. So triangle number 2 is going to look like this. Here's the A. This is now going to be B2 for the second triangle, C2. We had a side of 10 and 6 for the A and 24 degrees for the angle A. Now the question is, how do we find angle B2? if you did the following, if we did the sine of angle B2 divided by 10 is equal to the sine of 24 degrees divided by 6, and you solve that and work that out in the calculator, you would get that the B2 angle is 42.68 degrees. So the calculator is no help here. And the reason for that is because when you take the arc sine, you only get angles in the first quadrant if you're taking it of a positive quantity, which is what all these are. And clearly this angle needs to be obtuse. So how do we find the obtuse angle? Well, let me move this over here a little bit. The trick is to recognize where this angle actually came from. If I draw in the rest of what the triangle should have been from the previous part, then this side would have been 6 as well. And the angle B that we got is this one right here. So this was angle B. But because we have an isosceles triangle, these two triangles here on the right side of the figure, or the one triangle on the right side of the figure, both have sides of 6, then the angle B that's there on the right is also the angle B that's here on the left. And those two angles are supplementary. So B plus B2 is actually equal to 180 degrees. So instead of trying to do the law of sines again, it will not work. We know that it won't work. What you do is you just go ahead and use the information from the previous triangle, and you say B2 is equal to 180 minus the original B, and in this case that would be 137 degrees, 137.32 degrees. So you can't use the law of sines to get this first angle because it's not going to give you the acute angle. But we can use it for the rest of the things. So 137.32 degrees. So now we can find angle C. C is equal to 180 degrees minus 24 degrees minus 137.32 degrees. And that's equal to 18.68 degrees. And finally, we can find little c2 using the law of sines. So the sine of 18.68 degrees divided by c2 is equal to the sine of 24 degrees divided by 6. Cross multiply, we get 6 sine of 18.68 degrees is equal to c2 times the sine of 24 degrees. And c2 is equal to 6 sine of 18.68 degrees divided by the sine of 24 degrees. Work that out and you get 4.72. And that is the solution to both triangles. Finally, let's look at example 5. A UFO is spotted hovering in air by two different people. Bob sees the UFO through an angle of elevation of 31 degrees. Kat sees the UFO through an angle of elevation of 40 degrees. Bob and Kat are 16 miles apart, and the UFO is floating over the line between them. How far is the UFO from both of them? So let's draw a little picture. Here's the UFO. And here's Bob. And here's Kat. The angle of elevation to the UFO from Bob is 31 degrees. The angle of elevation from Kat to the UFO is 40 degrees. we know that the two people are 16 miles apart. We want to find out how far the UFO is from both of them. So I'm going to call the distance from Bob to the UFO X, and the distance from Cat to the UFO, we'll call that Y. I'll call the UFO's position U. And then let's figure out angle U. So we know that the sum of the angles of a triangle is 180. So 180 minus 31 minus 40 is equal to 109 degrees. Next, let's find the distance from the UFO to Cat. So we're going to use the sine of 109 degrees divided by 16 is equal to the sine of 31 degrees divided by y. Now remember, if you're looking for y, then the angle you have to use is the angle opposite y in the triangle. That's the 31 degrees. Even though the 31 degrees is more associated with Bob, it is associated with the distance between Cat and the UFO. So here we go, cross multiply. So we get y sine of 109 is equal to 16 times the sine of 31 degrees. So y is equal to 8.72 miles. And then let's go for x, which is the distance from Bob to the UFO. So we're going to again have the sine of 109 divided by 16 is equal to the sine of 40 degrees divided by x. And cross multiplying, we get x times the sine of 109 is equal to 16 times the sine of 40 degrees. And x is equal to 10.88 miles.